Hello everyone. Today we are going to be getting into lecture 9, derivatives. So let me give you a visual and also a definition of what derivatives are. So the derivative measures the instantaneous rate of change of a function. And you may recall that we have already seen this idea in the last lectures with tangent and secant lines. Specifically, when we're talking about the derivative, we saw it with the tangent line because the tangent line gives you the instantaneous rate of change. So I'm going to draw you a few pictures here, and hopefully we'll be able to understand a little better what's going on. So on here, I'm going to draw 3 identical graphs. They're supposed to be identical. And let's call this point x1, and let's call this x-coordinate x2. So we have an x2 and an x1. And here we have 2 distinct points, so they're different. And you draw the secant line through the 2 points. So if you recall, this gave us the average rate of change. This was our average velocity, if you recall, from a previous lecture video. So there we would have the secant line. Let's say that I'm going to keep x2 where it is, but I'm going to start scooting x1 closer to x2. So this space here, I'll call this h. It's a distance. So h equals x2 minus x1. It's basically the difference between these 2 points. And I'm going to decrease the distance now. I'm going to scoot x1 even closer to x2. So now it looks something like this. And I could grab the blue here and draw another secant line if I wanted to. Something like that. I'm not the best artist. I'm sorry. You should notice the slope of this line is actually greater than the slope of this line as we're approaching this point right here. And then eventually I can scoot x1 as far as I want until I get to x2. So then they both become x2. So you can think of this point as now merged into this point. And now here's the slope of my line through the 2 points, I guess, but it's actually just 1 point. And this is the tangent line right here. So this one is our tangent line. This only intersects the original graph in 1 point, whereas these 2 are secant lines because they intersect the original graph in 2 different points. So the idea of the derivative is you take this h and you're going to make it smaller and smaller until you actually have no h left, or h is 0. So here, h is 0. And we're going to use the idea of the limit to do this. And this is going to be our definition of the derivative. So let me write our definition down. So we have the derivative of f at x equals a is, and if I go to my picture here, I suppose I'm going to call x2 my a this time. This is the particular x value I'm interested in. So these x2s, they'll be called a. So this is, we'll call this the first one. So this is f prime, that's how you read that, f prime of a, which is the derivative at a, equals the limit as h goes to 0. So remember, h is just this distance that I'm shrinking, and eventually I'm going to make it 0. So that's where the limit comes in. This is f of a plus h minus f of a all over h. And that's provided it actually exists. Not all limits exist. So provided it exists. being the limit, provided the limit exists. There's another way that you can actually think about this. So we have an alternate definition as well. So alternatively, we could express it this way. The derivative at a is equal to the limit. And if I call this second point right here, this x1 that I'm scooting closer and closer to x2, if I call that b, so let's call that one b, then it's the limit as b approaches a of f of b minus f of a over b minus a. So notice b minus a, what did I call that distance here? That's actually just h. So this is just another way of thinking about it. It's, you can either take the 2 points and have one approach the other like this, or you can say, OK, h is the distance, let's make that go to 0. They mean the same thing. In some scenarios, the first one might be the preferable definition to use, and the second one might be preferable other times. It's just based on the calculations that you get when you use each definition. I'm going to use both of them at least once today, just so we can practice using both of them. But they're both more or less the same thing. So I'll just put a note here. So the derivative represents the slope of the tangent line and the instantaneous rate of change at x equals a. So again, I'm calling this x2 right here, that x1 is approaching. I'm going to call that special point a. So it's equal to actually both of these things. And my next examples, I'm actually going to start computing derivatives using the definition. So I'll see you in just a second. Welcome back. So as I promised, let's do 2 examples where we use the definition of the derivative to calculate derivatives. So the first one is find the equation of the tangent line to the graph y equals 1 over x cubed at the point 1, 1. So we know the tangent line will touch this graph in one spot. And this also means we're going to need to find the slope of the tangent line in order to eventually find the equation of the line. So this is a derivative problem in disguise. So what I'm going to do is I'm going to say the slope of the tangent line at x equals 1 is, and it's going to be our definition, I'm going to use definition 2 this time out of the 2 choices we had earlier. So that one was the limit as b approaches, and it approaches a. But this time I need to ask myself, what is the a I'm interested in? And that's this right here. The x value I'm interested in approaching is 1. So as b approaches 1, of f of b minus 1 over b minus 1. So that's me setting up definition 2. All right, let's run through the calculation here. So we have the limit as b approaches 1. F of b means I plug b into the original function. So I'm going to get 1 over b cubed minus, what is f of 1? Well, that's just 1 over 1, which is 1. This is over b minus 1. OK, so from here, what I'm going to do is I'm going to bring my limit over. I'm going to find a common denominator. So between 1 over b cubed and minus 1 over 1, my common denominator is b cubed. So this will be 1 over b cubed minus. This one I need to multiply by b cubed times, or b cubed over b cubed, just like that. So this will be b cubed over b cubed, which is equal to 1, all divided by b minus 1. So if I can continue over here, I actually have a lot more real estate over here than I realized. This is the limit as b goes to 1. I can combine these fractions now, and I get 1 minus b cubed over b cubed divided by b minus 1. This is equal to the limit as b goes to 1. I'm going to keep this fraction, change the sign, and flip this. You can think of this as just being over 1 if you want. Keep the first fraction. I get 1 minus b cubed over b cubed times 1 over b minus 1. I'll continue over here. So something that you need to know here is that this is a difference of cubes formula. You can use a factoring for this. So this is equal to 1 minus b times 1 plus b squared. That is the difference of cubes formula for this. So let me just write that down for you. This is the difference of cubes. Review the difference of cubes and the sum of two cubes factorings if you don't remember them. Then this is over b cubed times 1 over b minus 1. So this is the limit as b goes to 1 of. Well, I have a 1 minus b and a b minus 1, so they're just opposite of each other. So if I cancel these out, I'm left with a negative 1. So I'm going to get negative 1 plus b squared all over b cubed. At this stage, I can drop the limit, and now I can just plug in 1, because I'm not going to get anything that goes undefined here. So I will get 1 plus 1 plus 1 is 3 over 1. So this is going to be negative 3. So this is my slope. And I also have the point 1, 1 to begin with. This is an x and a y. So from this, you should just use your algebra 1 to get a equation of the line. So I'm going to use point slope form. It's y minus y1, which will be 1, m, which is negative 3, x minus x1, which is 1. So this is the slope, or not the slope, this is the equation of the line tangent to that original curve at the point 1, 1. Notice in this example, we really only used the y-coordinate for the very end. We plugged it in here. However, you didn't even need this, because you could have just plugged 1 in the original and found that yourself, right? So really, you didn't even need the y-coordinate this whole time. You could have done the whole problem anyway. So I'm just pointing that out. You can go to the original if you need a point. Sometimes they don't give it to you, so I'm just warning you. This one, we're going to find the derivative of f of x equals x cubed at 2. And I'm going to use definition 1 this time. So my derivative, I'll use definition 1 this time, just so you can see the difference between them. So the derivative at, and I'm going to say a, this one is the limit as h approaches 0 of f of a plus h minus f of a all over h. So for here, what I'm going to do is I'm going to go ahead and plug in some things. I need to plug in my a. So the a I'm interested in this time is 2. So this will be f of 2 plus h minus f of 2 all over h. I'll come over here and keep going. This is the limit as h goes to 0. I need to plug 2 plus h into my original function. This is going to give me 2 plus h cubed minus, if I plug in 2 into my original function, that's just 8 all over h. This becomes an exercise in foiling. You have to FOIL this all out. There's 3 of them, and you have to be careful how you do it. So I'm going to pretend I'm multiplying 2 of these together. So what I'm going to do first is this. I'll write it down here just so you can see my scratch work. But you're multiplying 3 of them in a row, and I'll just choose to do these 2 first, OK? Just to not drive myself crazy keeping track of everything. So this is going to be 4 plus, if I do these 2 inner ones, I get 4h plus h squared. And that's going to be multiplied by my third 2 plus h. I still have my minus 8 right here, all over h. So we just need to keep computing here. So this is the limit as h goes to 0. Here, this times this gets me 8. If I collect my h terms, I have 4 of them, and I have 8 more of them for 12 h's. If I collect my h squared terms, I have, let's see, 4 of them, and 2 more of them make 6. And then how many h cubes do I have? It's just the one at the end. So plus h cubed minus 8 all over h. I'll keep going right here. Just ignore that part. I'm going to go this way. This is limit as h goes to 0. 8 and 8 cancel. So when you're using this definition, if you notice that this f of a right here doesn't cancel, it usually means something went wrong, because that usually has to happen. So I ended up canceling this with something here. So that leaves me with 12h plus 6h squared plus h cubed all over h. The thing is now, is every single term in the numerator has an h. So I'm going to go ahead and cancel one h from all these terms because I'm dividing by this h here. So I'll have 12 plus 6h plus h squared. And now what I can actually do is I can plug this 0 in, because we don't get 0 over 0 or something over 0. We get 0 and 0 here, but we get 12 overall. So I can actually evaluate this. So you can think of this as the slope of the original function. And what does the original function look like? X cubed, I would expect you to have that one committed to memory. It looks something like that. And what does this mean geometrically, what we just did? If you go to x equals 2, so like right there at x equals 2, and you put a point on the graph, then the slope of the tangent line right there, it's pretty large. It's 12. So we found out that the slope of the line that only touches it in one spot right there, it's 12. You go over 1 up 12 at that instance in time. That's how fast it's increasing. OK, so it looks like from here, I'm just going to do a couple more typical examples of using the definition of the derivative. And then last, I'm going to talk about linear approximations. I'll give you one good example of that. So see you in just a second. Welcome back to this last part. I'm going to do one more example where I compute the derivative of a function. This time, I'm going to compute the derivative of radical x using the definition. I'm going to use definition 1 because personally, I'm more comfortable doing it that way. You can also try definition 2 and check and see if you get the same answer I do. You should. The difference here is I'm going to find the general derivative at a. So I'm not going to plug in a specific x value. I'm actually just going to plug in a when I'm done. And I'll have a general formula so that no matter what x is, I could plug that in later and evaluate the derivative. So let's go ahead and do this. So I'm going to use definition 1. So this is the limit as h goes to 0 of f of a plus h minus f of a all over h. And I mean, just to be nice and complete here, let me erase this and say that this is f prime of a, just to write it all out nice for us. And I am using the first definition of the derivative. So the derivative at a is equal to this expression. Let's write out what happens when we evaluate some of this. So if I plug in a plus h into the function, I get radical a plus h. All of it goes inside the function. Then I plug in a into the function, so that's root a, all over h. All right, so I need to keep going here. Notice I have problems. If I try to plug in 0, I get 0 over 0. Just like with those earlier indeterminate forms I was helping you with in the last video, if you see two radicals like this, use the conjugate to try to simplify things. So the conjugate here would be the first radical, a plus h, plus the second one. So you just change the sign in the middle. And to keep things equal, you need to multiply on the top and the bottom by the exact same thing. So I'm going to also multiply by plus here. And also, just like I pointed out last time, you'll go ahead and do the difference of squares on top. And then for this, just leave them written next to each other. So I'll do that right now. I'll just do h times radical a plus h plus radical a. That'll just stay on the bottom as is. Here, I multiply the first two together. What happens to the radical? It should just disappear. So I get a plus h. Notice here, I'm not going to write it, but this, the two outer ones, and then the two inner ones are just opposites of each other. So this is positive, and then these are negative. So they're just cancel. And the last two you need to multiply would be root a times root a. And this one has a negative in front of it, so this is minus a. If I simplify this, oh, this is, aha, I just noticed that. If you simplify this, you have a minus a on top. It just gives you h over h radical a plus h plus radical a. And then, thankfully, I have a factor of h and h in the numerator and denominator now. So I have the limit as h goes to 0 of 1 over, cross those h's out, radical a plus h plus radical a. And the last thing I need to do is plug in 0 for h. So this is going to be 1 over radical a, and I just have 0 here, plus radical a. I'm going to go ahead and add those together. You can add radicals if they have the same thing on the inside. So this is 2 radical a. And this is my general derivative. So if I wanted to know what is the derivative at 1, the derivative at 1, x equals 1, I'd plug in 1 for a and plug in 1. So I'd get 1 over 2 times root 1, which is 1/2. So the derivative of this function at 1 is 1/2. And I can pick any number I want, as long as it's defined. You shouldn't plug in -5, because the function is not even defined at -5. But for all these positive values, you could plug in now and find any derivative value you wanted. So it's nice to have just the general one sitting here. OK? Let's talk about linear approximations a little bit. So I'll just put a note here. So the derivative is a good approximation. I'll put APPROX for approximation for the change in f of x for small values of delta x. And this is just the difference in 2x values. So if I'm moving from x1 to x2, delta x is just the difference, how far you moved. It's h, basically. This is also just h that I was talking about earlier. So visually, if you're a visual learner now, let's go over here, and we'll draw a picture. I'm a little bit more of a visual learner myself, so I like a picture. We'll draw this nice function here. Let's say that this right here is going to be a. We'll say this is the x value a, and then this one right here is going to be a plus h, and this distance is h. So if we start with a tangent line, and we just draw the tangent line at a, it would look something like this. So our tangent line says the value would be here at a plus h. And it's actually supposed to be here. So this is the error. It was an underestimate. But this line right here, it's a pretty good estimate of what the actual function should be. Just in case we didn't know its formula or something like that, we could take this tangent line, and this is how close we were to the actual value. So if you're very close to where you're estimating from, then the tangent line is a pretty good estimate. If you pick a value that's very far away from your tangent line, it becomes worse and worse. So this is the visual that I want you to have in your mind. Our approximation formula, I'm going to write that on the board for us here. Make sure you have this in your notes. So this is kind of our approximation formula. So f of a plus h, so the value at the new position is roughly, I'm going to put these wiggly lines for roughly where you started at f of a plus the derivative times h, where h is that distance you had to move to the new point. OK, let's do an example. So let f of x equal the square root of x. Use the equation of the tangent line, so of the tangent line, to, oh, I'm not done with that yet. So use the equation of the tangent line at x equals 4 to approximate, I'll abbreviate it again, approximate x equals 4.2. To approximate f of x, to approximate the value, so approximate f of x at x equals 4.2. OK, so let's start using this formula here. So f of a plus h is approximately f of a plus f prime of a times h. We're going to go on a mission right now to find all these pieces and where you get them from, OK? So let's go do that right now. First thing I'd like to find is h. I think that h is pretty easy. So for h, you need x2 minus x1. You need the difference in where you started for x and where you're going. So we started at 4, so my x1 is 4. And we're going to go to 4.2. So that's my x2. So h is 0.2. It's positive because we moved in the positive x direction. We moved from 4 to 4.2. It's important that you get the correct sign because that actually matters. So you need to start from 4, go to 4.2. That's an increase. So right here in my formula, I'll fill that in as 0.2. And this h also is 0.2. OK. A is where you started. So this a in the formula will be 4. That's the x value where I started. So this is 4. My f of a is going to be f of 4. And I need the derivative at 4 as well. So now I've plugged in all of my a's and all of my h's. Let's decipher this a little more here. So this means f of 4.2 is roughly, and remember, this is where we're trying to estimate now, so this makes sense. So we're going to approximate at 4.2. What is f of 4? Well, the function they gave us is radical x. So I'm going to plug in 4, and I'll get 2. So I valued 4 here. What is the derivative at 4? How would you know that? Is there something on the board, maybe in the last problem, that would tell you how to get that? You should jump over here and realize that we did this. The derivative at 4 of the square root function, we calculated it. You want to plug in 4 into our answer we got right here. It'll be 1 over 2 root 4, which is 1 over 2 times 2, which is 4. So this right here, we use the last problem, and we know that this is 1/4 times 0.2. Now this expression over here, this is equal to 2 plus 0.05. I just took 1/4 of 0.20. And then this is 2.05. So this is an approximation for what this is actually equal to. So we approximated radical 4.2. This is equal to probably something else. This is probably an underestimate. I don't have a calculator handy, and I'm not like a genius or something. So I don't actually know what that is to like 6 or 7 decimal places. But if you put it in your calculator right now, you'll see that it's probably very close to this. It's probably just a little bit greater than this. OK, so that's how you can use tangent lines to approximate values very close to the tangent line. OK, so with that, I'm going to end lecture 9. Make sure you do your quiz. Make sure you do your Kronos homework. Send me questions. I will see you next time. Bye.